My name is Chang Gun. I'm from University of South Florida, and I'm in industrial engineering department. So I have no background in mathematics or computer science, but the topics are somehow related to somehow in computer science. So for the most of audience, I guess the most important lesson from this seminar is going to be the word itself, the satisficing. So I'll be talking about that weird word, satisficing, a little bit, and related mathematical concepts in network equilibria. So in traditional economics, an economic person or a perfectly rational person are defined with two properties. The first one is a clear system of preferences, and second one is the knowledge of the decision environment. And so that means that every economic person that exists in the economics textbook have those two properties. But in reality, not all decision makers are perfectly rational as assumed in economic literature. So often people have a lack of strong personal preferences. So for many of us, it's very important to decide which one to eat for their lunch. So people are just confused with which one today, which one tomorrow. So sometimes people don't have really strong preferences. That means that their preference cannot be really strictly ordered, or people themselves do not have any idea about their own preference in the ordered list. Or for the second one, a lack of full information about the environments. So because of these two reasons, Simon is a pioneer in this field of economics. It's called behavioral economics. Introduced new concepts like boundedness and rationality. So people are rational, so there's no doubt. So people are rational, but not perfectly rational as defined, assumed by economists, but somehow boundedly rational. So Herbert Simon argued there are two main sources of boundedness and rationality. The first one is satisficing behavior rather than optimizing. So that means that instead of choosing always the optimal solution for any decision, as long as it is somehow satisfactory, then they choose that alternative. Or in the second source is each individual's perception of the decision environment. Instead of having the perfect knowledge or complete information about the decision environment, they often have just their own perceived version of the environment. So working with these two things, Herbert Simon created some new field of study called behavioral economics. And the most importantly today, definition of relatively new English word is a combination of satisfy plus suffice. So that means that optimization is talking about the real optimal solution. But satisficing is talking about something good enough. So something good enough is called some alternative whose reward is above a certain threshold, usually called an aspiration level, or just close enough to the best possible reward. So people in reality have some rationality, but not always optimizing, just satisficing. So I'll be talking about satisficing here, but I will try to connect the satisficing with perception. So how those two main sources of boundedness and rationality are connected with each other. In the context of path finding, suppose there are 3 passes from home to work. So one pass taking 10 minutes, the others 14 and 12. So for these 3 passes available, so people may have chosen 12-minute pass instead of 10-minute pass. So suppose we just observe this person's decision, and that decision was 12 minutes instead of 10 minutes, which is optimal. So for that one, we can have 2 different explanations according to Simon. So first one is that this driver does not optimize, just try to satisfy. And second reason is that this driver is an optimizing decision maker, but this driver had some perception error in their information. So these 2 explanations are different, but just try to explain why this driver chose 12 instead of 10-minute pass. Okay. So mathematically, if we just try to describe what I explained for pathfinding. So we can work with a new variable x. Oh, sorry. A variable xij. Say suppose xij is a binary variable for a link ij if a link ij is chosen in the path. So in the context of network optimization, we can describe the feasible path choices with this set x, and in the shortest path problem, we just try to minimize Cij times Xij in this summation. So we just let its minimum value as C0. So C0 is the length of the shortest path. So when C0 is available to the, say, observer of the system, say we are observing some system and some these drivers decision making, then we will compare actual choice of driver with our knowledge of C0. So one way to describe the behavior of satisficing is additive satisficing. Say a driver will choose some path described by vector x if Cij times Xij summation is less than or equal to C0 plus certain positive number E. Suppose E is equal to 5 minutes. Okay. So as long as a path's length is less than the difference between the chosen path and the optimal path is within 5 minutes, then drivers will choose that path. Or differently, we can describe with a multiplication form. So 1 plus kappa. Suppose kappa is like a 0.1, 10%. If there's a less than 10% difference, then it's okay to choose. In another model, just there is a satisficing, and I also talked about some second source of boundedness in the rationality as a perception error. Say suppose a driver is an optimizer, but this driver has his or her own perception of travel cost, Cij. So for each link Cij, Cij is a real travel cost, but Cij minus epsilon ij is perceived cost of travel for ij. So we can describe, say, optimizing decision maker with perception error by this problem. And epsilon ij is some vector from some set. Okay. So by utilizing this model, we can describe the second source. But when we design this epsilon, we do not know which epsilon will be used by a certain driver. So epsilon itself is some uncertain parameter to the observer, okay, to us. We are observing some system and some driver, so we are observer. But we can probably come up with some set that this vector, uncertain vector epsilon belongs to. And so here's my suggestions. So we can probably come up with, say, a summation of epsilon ij is restricted by certain parameter E. Okay. So driver has his or her own perception error, but its total amount of perception error is limited by a certain parameter, certain number, constant. Or each link ij has some range. This is summation. In these two forms, this summation is restricted, and its link ij is restricted.
Do you have a reason why you chose these errors to be non-negative?
It was easier to work with in the proof I wanted to show. So as you said, there is no really good reason, but I can make a good connection with, say, first source is a satisficing, second source is the perception error. So I just wanted to try to unify these two approaches in one single frame, and these sets worked very well. So we can consider two drivers. Say driver A doesn't care about the shortest path as long as her path is within 5 minute difference with the optimal path. Or driver B cares about the shortest path, but based on his own perception of link travel cost. So two different persons, two different decision makers. But the raw choice decision made by drivers A and B can be shown to be equivalent, mathematically equivalent under certain conditions. Of course, the sets I introduced. So driver A is a satisficing driver with precise perception, and driver B is an optimizing driver with imprecise perception. Okay. So in one way to compare two drivers is through this theorem. Say So driver A is an additive satisficing decision maker. So the choice vector, the path vector x bar is chosen as long as it is additive satisficing. But we can also show that with using this same E in this set E, we can see two models, satisficing model and perception error model, can produce the same set of passes in overall. Of course, each individual path choice will be different, but as a whole, the sets are the same. Similarly, we can show this part, 1 plus kappa and kappa over here. So kappa is a multiplication form. Or we can, more interestingly, we can also introduce subpath multiplicative satisficing. Just like in the shortest path problem, we have a property of subpath optimality. So we just can also define subpath satisficing path. Say any subpath of entire path is a satisficing path instead of optimal path as a subpath. Just like in this example, say 1 is the origin and 4 is the destination. No, 3 is the destination. So we can go to 1, 2, and 3 or 1, 2, 4, 3. So 1, 2, 3 and 1, 2, 4, 3 are two satisficing passes with kappa equals to 0.1. But if you just consider 2, 2, 3, there is two subpasses, 2, 2, 3 or 2, 4, 3. So 2, 4, 3 is not satisficing path. So the entire path 1, 2, 4, 3 is not subpath satisficing. So we can consider those properties. Then if we consider this set, then we can show that perception error model and satisficing model can produce the same set of passes. So this set is pretty interesting because I'll be using this one in more complicated form. And this has a more usefulness in other areas. So far, I only talked about when Cij is a constant. Cij is constant. But in real traffic network, say Daejeon City, there are many people arranged and the congestion is there. So whenever more people are traveling through the same city, same link or same road, then there occurs some congestion, meaning that, say, Cij was just without any traffic, it was like a 10 minutes, but it can go up to like 20 minutes, 30 minutes. So it's congestion. So Cij was constant, independent from the route choice of the decision maker. But now we can consider Cij as a function of route choice of persons. My background is in transportation and traffic engineering. So I rely on some information from Bureau of Public Roads in the United States. But different areas have different, delay functions. In computer science or telecommunication is a different form, but just road management, this form of a function is popularly used. So Cij is a travel time, and tau ij is free flow travel time, and Vij is the flow in ij, so number of cars in link ij, and Kij is the capacity of the road. So as soon as Vij exceeds the capacity Kij, then travel time increases very quickly, and 0.15 and the power 4 are determined empirically. So, but nobody knows how accurate this is. Actually, this was suggested in early 70s, and people are just still using it. But but anyway, some function like this, some polynomial function like this form, we can consider Cij as a function of Vij. So tau ij is just constant, and Kij is also constant. Kij depends on the shape of road and how many lanes and the curvature and so on. Okay. But anyway, so Kij is also constant, so only Vij is a variable. So one question now is related to satisficing. So if everyone satisfies, so every driver in the city is a satisficing driver, the performance of the total system will be different from optimizing equilibria. So I was interested in how bad can the system performance be. So compared to when everyone is just trying to optimize, if everyone tries to satisfy, the total system performance can be worse or better, but in the case of worst case, how bad will it be? So in traffic engineering, so this is a map of Sioux Falls. It's a city name called Sioux Falls in South Dakota. It's a very small town. And this, for some traditional reason, this city's network is very well used in some computational study of traffic equilibria. And in this equilibria, I tested it. So this one, so this, the horizontal axis is for kappa. So kappa is for satisficing percentage. So if it's, when it's 0, say usual equilibrium, people form some equilibrium, and this is called the usual equilibrium. And the system performance was about 74.8. And of course, it's a constant. And as kappa increases, the total system performance, as people satisfy, the total system performance can be as bad as like a 79 when kappa is 1. Okay. Of course, kappa is 1 is very big number, but anyway, it has some range. Also, it can be better than the usual equilibrium, okay, when people are optimizing. So when people are optimizing, I call the resulting usual equilibrium as a perfectly rational usual equilibrium, as opposed to satisficing usual equilibrium, M for multiplication, multiplicative satisficing usual equilibrium. So we can have some range. So this one I obtained by some numerical computation for this specific network. But for any general network, how bad can this line go up? So will this line go up this much, this much? What's the really the ratio? So that's the interest. That's the problem I want to address here. So we first need to consider how to define the usual equilibrium. So in traffic engineering, there's some traffic engineer called Wadrov. He defined some properties for usual equilibrium. Say a path is taken only if its travel cost is the minimum among alternatives. So assuming that drivers are optimizing decision makers, say FP, flow for path P is strictly greater than 0, implies, so you observe some traffic pattern and FP was strictly greater than 0, that implies the path cost for that path P must be the minimum among all available alternatives. And or alternatively, we can also do, consider, say, certain path P's travel cost CP is greater than the minimum, mu W. W is the OD pair, origin destination pair, or in more discrete math term is source and sink. And if it is not optimum, minimum, then there must be no cars traveling along that path P. Okay. So with these two properties, we can form some other properties as well. And as an example, say this is a very simple network. So there's an origin O and destination D. And for this travel, this path, travel time is fixed as 1. So regardless how many cars traveling, the travel time is fixed. And this one has C2 as equal to V2. It's proportional to V2, the traffic volume in this link. If we consider travel demand from origin to destination 1, the usual equilibrium is as no cars on this link and all cars are traveling on this link. Then we can make travel time equals to 1 here, 1 here. So it's equilibrative. So it's the same. And then we can consider the total cost as equal to 1. So 1 times 0 plus 1 times 1 equals to 1. But for the system developer, system operator, this is not optimal. So we can also consider system optimum. Say out of total of 1, we can route a half here, a half here. In this case, travel time in this link is 1 still 1. So 1 times a half. And travel time in this link becomes a half. So a half times a half. So total cost becomes 3/4, which is less than 1. So usual equilibrium cannot guarantee the system optimum. So drivers are trying to optimize their own route, but it can be far from the system optimum. so which is not good for the, say, city government or system operator. So in most cases, we want to try to achieve somehow system optimum, but not always possible. So the gap between the usual equilibrium, system optimum exists. Okay. So traffic assignment is talking about how to optimize that. So we have constraint like FP, summation of FP, so this is path flow, equals to the travel demand for that origin destination pair, W. And PW is the set of all passes available for that origin destination pair, W. And we can distinguish usual optimum and, or usual equilibrium with system optimum flow. Okay. So there are two different kinds of flow patterns we can consider. So system optimum, we want to try to minimize the CP times FP. But usual equilibrium just defined with some definition, but we can also form some special program called a variational inequality problem with this, say, travel demand constraint with this form. So we try to find F0, a vector F0, such that CP times F0 times FP minus FP0 is greater than or equal to 0 for all all vectors F in the set F. So this is a special form of inequality, but inequality must be satisfied for all elements of this vector space F. So, so this inequality itself varies, so it is called variational inequality, and it is related to equilibrium problems, many different equilibrium problems, but in general anyway, so we can just define F transpose X minus X0 greater than or equal to 0. So this is a variation inequality in finite dimensional vector space, but we can also consider infinite dimensional vector spaces, but we will restrict our attention to finite dimensions. So for the same traffic pattern, we can consider path flows, so the set of path flows F, but also we can consider, we can describe the same traffic pattern for a link volume. Link traffic volume via VA here. So A is arc. So VA as a summation of FP that pass through that arc A. Or we can also distinguish, split this VA into XAW. XAW is a link volume at A with origin destination W. Okay. So we have three different ways of describing the same pattern. So FVX. And I also define travel time functions. So travel time functions are defined as TA. So link arc A, we have TA with traffic volume VA. So travel time is a function of traffic volume. And we have a performance function, ZA. So ZA VA is equal to TA VA times VA. And for this performance function, we can consider path-based performance function. So this is path travel time, CP, and multiplied by path flow volume, FP. And we can also consider the relationship between CP, path cost, with TA, the arc cost. Then eventually, we consider its summation of GAs, which is a ZV, or equivalently CF. In path form, this is a link form, this is path form. So two different ways. So this function, performance function value is called a total system travel time. So we will compare this total system travel time in two different patterns, system optimum and usual equilibrium first. So we work with perfectly rational usual equilibrium F0. F0 as defined by this relationship when people are optimizing decision makers. So drivers are optimizing, and there is some resulting equilibrium pattern, and the name is perfectly FRUE. Of course, they can be written as a variation inequality in terms of path flow or link flow, or link flow with OD information, as in X. Okay. So we will just play with this one with help from this one. So usual equilibrium is a Nash-like equilibrium because in usual sense of Nash equilibrium, there are n different number of players. But in our problem, there is a flow rate. So a flow rate can be any real number. So we cannot really distinguish one player from another player. But the concept itself is very much same. So sometimes the usual equilibrium, the traffic usual equilibrium is called a non-atomic congestion game problem. So non-atomic means that we cannot really split for each player. Anyway, for the same setting now, we can also consider traffic flow pattern when drivers are satisficing. So a path P is chosen, so strictly greater than 0, meaning that someone is using that path P. So that implies that the path cost from that path P is less than or equals to 1 plus kappa times the minimum value. So they are satisficing. So drivers are satisficing with some factor kappa. We don't know the value, but we can assume. So with these notions defined, so I will call the resulting traffic pattern as a satisficing usual equilibrium as opposed to just usual equilibrium. And we can consider the notion of price of anarchy. So the price of anarchy compares the system optimum and the usual equilibrium. So in this same example, we had this computation, the difference from the usual equilibrium and the system optimum was the ratio 4/3 in this case. And this 4/3 happens to be, it's called a price of anarchy, and it actually happens to be the worst case price of anarchy. So price of anarchy meaning that there's no control. System optimum meaning there's a control, and usual equilibrium meaning there's no control. So anarchy means there's no control, so price of anarchy. So 4/3 happens to be the worst case ratio between the usual equilibrium performance and the system optimal performance when the travel time functions are linear. And similarly,
so that works for any network.
Any network. Okay. For any network instance, as long as the link delay functions are linear. And for general polynomial of order P, we can compute the worst case performance. Worst case price of anarchy as this one. So when P equals to 4, it's about 2.1. This is not my result, but this is a well-known result in computer science literature. And there is a notion of satisficing. So when we have a satisficing usual equilibrium F kappa, we can also compare F kappa with F star. F star is the system optimum traffic pattern. So the ratio between CF kappa, satisficing usual equilibrium, to CF star, the performance of system optimum. So this is also called price of anarchy with approximate Nash equilibrium in the computer science literature. Okay. So F kappa, the definition of approximate Nash equilibrium coincides with satisficing usual equilibrium. So we can also consider the price of anarchy of this F kappa. Then we can find, say, for the range of kappa, say kappa is sufficiently large, is larger than a certain number, then it becomes 1 plus kappa to the power of n plus 1. And when kappa is smaller, we can show this weird number. Okay. So it's a function of n. N is the order of travel time polynomials. So when n equals to 1, we have this fractional number when we have 1 plus kappa to the power of 2. And when n equals to 4, we have 1 plus kappa to the power of 5, and with this fraction. So this compares, this is the price of anarchy, comparing satisficing usual equilibrium with system optimum. But my interest lies in the comparison of usual equilibrium, satisficing usual equilibrium with perfectly rational usual equilibrium. So two different types of usual equilibrium, but how to compare them. So price of satisficing is comparison between C, F kappa. So F kappa is satisficing usual equilibrium. F0 is a perfectly rational usual equilibrium. So two different types of usual equilibrium. So F0 is when people are optimizing. F kappa is when people are satisficing. So how to compare that? What is the worst case ratio? So again, to the simple example with slight difference here. So here I have a 1 plus V1 as travel time function. Here I just fixed at 1. So usual equilibrium becomes 0 here, 1 here. Then the travel time becomes 1 and 1, the same. So it's equilibrium. And total cost becomes 1. And if we consider satisficing usual equilibrium, so at the usual equilibrium, travel time for both passes will be same. But in the usual equilibrium, it can be different, but not very much different until, with some restrictions. So V1 was 0. So V1 was 0. So no cars traveling in this link. But I will move some of those to V2. So I move by amount by delta. So V1 becomes delta, and V2 becomes then 1 minus delta. And if delta is less than or equals to kappa, then both passes becoming satisficing passes. So we maintain satisficing usual equilibrium. So the total cost becomes Z delta, which is delta square plus 1. So if we consider the worst case for this network, then it becomes 1 plus kappa square. So in this network, 1 plus kappa square is the worst case price of satisficing. The ratio between the satisficing usual equilibrium and the perfectly rational usual equilibrium. So coming back to price of anarchy. So we can learn from price of anarchy somehow. So maybe better explained with this graph here. So if kappa, so this is when n equals to 1, so linear travel times. When kappa is above 1, then 1 plus kappa square becomes the price of anarchy and also the price of satisficing. And when kappa is less than 1, then we know it is at least 1 plus kappa square and at most this number, so the red line, somewhere in this shade. But we do not know what exact value is. But this red line cannot be the exact price of satisficing, because when kappa is 0, satisficing becomes optimizing. So this red line must go to 1 here. So red line cannot be the exact value. Well, Christodoulou et al. In 2011 found some interesting example that this blue line becomes exact in this area, but not exact for this area for the price of anarchy. Okay. So this paper by Christodoulou et al. Is talking about price of anarchy of satisficing usual equilibrium with this interesting example. Say suppose k equals to kappa equals to 0.5, then we set m equals to 3 and k equals to 2, so that m over k gives a good, exactly in this case 1 plus kappa. So we have 5 nodes here, and this is an undirected graph. Say there's a origin destination pair from 1 to 3 and 2 to 4, no, 1 to 4 and 2 to 5 and 3 to 1, 4 to 2, 5 to 3. So there are 5 different origin destination pairs. Then the link travel time is equal to VA to the power of n. So n is any order. Then in this case, they found that the usual equilibrium happens to be everyone traveling clockwise. And at the system optimum, everyone travels counterclockwise. So then comparing the performance of system optimum and usual equilibrium, they found that in this line becomes exact. But anyway, we also found that in this example, for all range of kappa, the price of anarchy becomes 1 plus kappa to the power of n plus 1. And for the same example, it also, the price of satisficing also happens to be the same number. So we just took one lesson. Price of satisficing, the worst case price of satisficing is at least 1 plus kappa to the power of n plus 1, because we have an example. Okay. So but is it going to be exact one? So we don't know. Okay. We don't know. So I tried some attempt, and I showed that under some additional condition, this becomes exact. Okay. So the sketch of proof is I will first comparing the performance of f kappa. This is a satisficing usual equilibrium. And I will compare this f kappa with f0, but 1 plus kappa times f0. So f0 is a the perfectly rational usual equilibrium, but just multiplied by 1 plus kappa everywhere. For every element, I multiply 1 plus kappa. Then I can show this inequality under certain conditions. And then this comparison is pretty straightforward, because C is a polynomial of order of n plus 1. So 1 plus kappa times n plus 1, this ratio becomes obvious. And then if you compare CF kappa and CF0 here, then we obtain 1 plus kappa to the power of n plus 1. But to show this one, we need a bit of work. So first thing I do is multiply 1 plus kappa, some factor, to everywhere, to every path P, and every path flow is multiplied by 1 plus kappa. That means that we are flowing 1 plus kappa more flows to the system. So I define the set of feasible flow vectors F1 plus kappa. And similarly, we can also define V of 1 plus kappa and X over 1 plus kappa and so on. So I'll be using hat, F kappa for multiplied 1. So F hat kappa is satisficing usual equilibrium with the increased travel demand. And just without hat, F kappa is satisficing usual equilibrium in the original system. And then I will be comparing F hat kappa with F kappa. And to work with that one, again, I have to introduce the perception error in the usual equilibrium. So we consider the same usual equilibrium concept. So when people are optimizing, so people are optimizing, but based on their own perception error. So instead of the real trivial delay function TA, different people have a different perception of travel time, say slightly smaller than that. So it can be as large as 1, lambda A is some constant, some unknown constant lambda, but belongs to a certain interval. So we do not know a specific value of lambda A, but we know the range of lambda A. So drivers of perception are related to the original trivial time function TA, but different. And then we can show that the resulting trivial pattern from this equilibrium problem becomes satisficing usual equilibrium as defined earlier. So usual equilibrium based on perception error in terms of this vector space V implies satisficing usual equilibrium. So what I do is, so if F0, so I need to make a connection from F0 to F kappa. So F0 is a perfectly rational usual equilibrium, and F kappa is a satisficing usual equilibrium. I need to make some connection to compare. But I show first that F0 is a perfectly rational usual equilibrium in the original system F, and 1 plus kappa times F0. So F0 is given, then I just multiply F0 by 1 plus kappa in every element. Then I obtain satisficing usual equilibrium in the increased space F1 kappa. So I just made some connection with usual equilibrium with satisficing usual equilibrium. So proof can be done by the previous theorem. Then we can also compare F0 and F hat 0. So F0 is a perfectly rational usual equilibrium in the original system F, and F hat 0 is a perfectly rational usual equilibrium in the increased trivial demand F1 plus kappa. Then we can observe this relationship. So CF0, performance of F0 is less than or equal to CF hat 0, but not just less than that. So 1 plus kappa times CF0 is less than or equals to CF hat 0. I mean, this sounds natural, right? But can you obtain a similar result comparing F kappas? So satisficing usual equilibrium can be better than F0 or worse than F0. F hat K kappa also be better than F hat 0, worse than F hat 0. But can you show this? So CF0 is here. Then we know that CF hat 0 is here. There exists obvious gap between these two by factor of 1 plus kappa. So we know this. But we consider CF kappa, the performance of satisficing usual equilibrium, we know that it can be better than CF0, it can be worse than CF0. So it can have some range here around it. And also if you consider satisficing usual equilibrium in F1 kappa, so when the treble demand is increased, so CF hat kappa can be better than CF0, F hat 0, or worse than CF hat 0. So it can have some range. So we have two different ranges here. Do these two ranges have some overlaps or not? Okay. If they do not have any overlap, then we show this relationship for any F kappa, for any F hat kappa. So this was the most difficult problem for me, and I tried my best, but I couldn't show it globally, but under some additional condition. So I had to introduce some weird condition over here. So when F hat kappa, F hat sigma is similar as a kappa, so sigma is 1 plus kappa to the power of n minus 1, and F kappa maintains this relationship, then we can show this. Okay. Then the rest of the proof is becoming very obvious. But the real problem is now, what does this condition mean? Okay. I'm stuck there. So if you compare now, so under this condition, we can compare CF kappa and CF0. So the price of satisficing is bounded above from 1 plus kappa to the power of n minus 1. So we obtain just worst case condition. So we have a strange condition. So this condition says the difference between the travel time, past travel cost, times the difference between the travel flow itself is greater than sigma, is a function of kappa, times something. These two terms are positive terms, but it's multiplied by something. In the theory of variation inequality, we define monotonicity of functions Cp. So if this relationship is satisfied, so this form and this form is similar, if this form, this multiplication is greater than or equal to 0 for any f1 and f2 from the set f, then we say it is monotone. And if it is strictly greater than 0, we say it is strictly monotone. And if it is greater than or equals to alpha times the norm of f1 minus f2 square, then we say it is a strongly monotone. Okay. So this one looks like somehow related to strong monotonicity, but this condition is talking about two different flow vectors f hat sigma, f kappa from two different vector spaces. But this strong the definition of strong monotonicity is talking about the same vector space f, so slightly different. So my best guess is somehow this condition is related to this strong monotonicity, but I am uncertain. Okay. So again, I tested if this condition really satisfied or not in two different examples. In example 1, a simple example, in this link it is fixed at 1, and the second link is strictly increasing, 1 plus v2. In the second example, we have both v1 and v2, both link travel times are strictly increasing. So for this first example, I could not find any kappa or sigma value that satisfy this condition. But in second example, when both link travel times are strictly increasing, I was able to find the range of kappa that satisfy this condition. So I mean, for now, my guess is that this condition is related to some monotonicity, strict monotonicity, but the exact meaning, I don't know. So again, coming back to the numerical example. So I obtained the usual equilibrium over here. So this is a perfectly rational usual equilibrium, and this is the worst case usual equilibrium, and this is the best case usual equilibrium. I mean, worst case satisficing usual equilibrium, and worst case satisficing usual equilibrium. I mean, this best case. And the question is, how did I compute this? So again, I had to use sensitivity analysis in the the theory of variation inequality, because the satisficing usual equilibrium is related to some perturbed variation inequality. So I played with some sensitivity analysis and devised some algorithm to compute this. But anyway, I computed these values, the worst case, best case, somehow. Then I have some theoretical result on the upper bound on this worst case. And if we compare, actually, this is the theoretical bound, 1 plus kappa to the power of 5. And we can barely see the numerical value here, almost same, which means 1 plus kappa to the power of 5 to the 1 plus kappa to the power of n plus 1 is a theoretical value that exists in very weird example. But this theoretical bound is too big to be used in actual network, some practical network. But anyway, I mean, this can happen. This can happen. So this is the end of my talk, and I want to ask your help. If you ever see anything similar to this condition, or if you capture any implication of this condition, please let me know. Thank you.